Muy bien. Bueno, pues muy buena tarde al auditorio, al público aquí en el INAHOY y a todos los que nos están siguiendo de manera remota. Estamos muy contentos porque el día de hoy nos va a acompañar en esta sesión extraordinaria del seminario institucional el doctor Marco Leeuwen. Él es spokesperson del experimento ALICE, de los 4 experimentos más importantes en el Large Hadron Collider, que es parte del Centro Europeo de Investigación Nuclear, el CERN. Bueno, para darnos la bienvenida oficial, me permito saludar a la doctora Claudia Feregrino Uribe, nuestra directora es encargada de los asuntos del despacho de la Dirección de Investigación y de la Dirección de Desarrollo Tecnológico.
Gracias, Daniel. Buenas tardes a todos. Es un gusto que estén aquí con nosotros en este seminario y voy a hablar en inglés por nuestro invitado. On behalf of the Acting Director, General Director of the National Institute of Astrophysics, Optics and Electronics, we warmly welcome Dr. Marco Leeuwen. We are truly honored to have such a distinguished expert to share their insights with us. Today's seminar reflects the forefront of developments of the ALICE next generation experiment to study the quark-gluon plasma at Large Hadron Collider at CERN, and promises to inspire further discussion and exploration. I encourage all of you to engage actively and make the most of this unique opportunity. Thank you, Dr. Leeuwen, for being with us today.
Just showing, I will just introduce, also switching to English, and I hope everybody can follow. I'll just introduce shortly our prominent guests today. So Marco Leeuwen, as I said, ALICE spokesperson, has a research that focuses on the strong interaction and the formation of quark-gluon plasma in high-energy heavy ion collisions. He received his PhD at NICEF and Utrecht University, working on the measurement of kaon production and search for open charm in the Na-49 experiment at the SPS. He was postdoctoral fellow at Lawrence Berkeley National Laboratory, working in the STAR experiment at the Relativistic Heavy Ion Collider, where he worked on high transverse momentum physics and the study of parton energy loss in the QGP. During this time, he contributed to the proposal for the electromagnetic calorimeter, MCAL, in ALICE. He moved back to the Netherlands in 2007 and has been working on the ALICE experiments since then, with a focus on jets and high PT physics at the LHC, the Large Hadron Collider. He has been awarded the NWO VC Research Grant in 2018, and he has been playing a leading role in the ALICE focal calorimeter upgrade project, which will be used to probe the low X structure of the nucleus with direct photon production. Marco served as ALICE physics coordinator from 2017 to 2019 and as upgrade coordinator from 2020 to 2022, and currently is, as I said, the spokesperson for the ALICE experiment. So welcome, thank you very much, and we will all enjoy your wonderful talk, I'm sure. Please go ahead.
Yeah, thank you very much. I'm happy to be here and happy to see so many people. I realize that this presentation is maybe a little bit out of your regular wheelhouse. I'll try to give a bit of introduction in the field that I'm working in, but a large part of the talk also focuses on instrumentation, on particle detectors, which you will see or have maybe already heard have a lot in common with astrophysical particle detectors. So I think that is where we really connect the fields, basically. Now, to introduce this, I would like to say a few words about the standard model of particle physics, about interactions between particles. Now, what you see here on the left, you're familiar with. This is a picture of an atom. You probably also know that there are electrons that surround the nucleus. Electrons, in fact, are fundamental particles, but the nucleus, the atomic nucleus, contains protons and neutrons, which are not fundamental particles. Protons and neutrons actually consist of quarks. And for protons and neutrons, these are the up and the down quark. And the research in ALICE focuses on the strong interaction, which involves quarks and gluons. So here on the right, I show you what we call the particle content of the standard model of particle physics. So this is all the fundamental particles and interactions. You see here in blue, I highlighted the electron and its heavier siblings. We together call them leptons, the muon and the tau lepton. Then there are the neutrinos, which are closely related but don't have charge. Those particles have only electric charge. Now they interact via, in a quantum field theory, the electromagnetism is described by photon exchange, as you may know. Now, and as I said, what my research focuses on are the quarks, where the up and the down are the lightest ones that are in the protons and neutrons, and then the heavier ones, charm, strange, bottom and top, and they will come back into in the rest of the presentation. And the gluon is the exchange particle. It's like the photon, but for the strong interaction. And what we study in heavy ion collisions, which is the main part of the research that we do in ALICE, is the bulk matter of the strong interaction. And I'll try to explain a bit more how that works. And to do that, I wanted to introduce this in terms of energy scales and temperatures. And since we got to talk about matter, temperatures are important, but they're, of course, related to energy scales. So as you probably know, the ionization energy for an atom can be as low as 5 electron volt, and it can go up quite substantially for heavier nuclei for the inner electrons to 100 kilo electron volts. And this are temperatures of 10,000 to 10 million, 1 billion degrees Kelvin. Then the next interaction that we can think about is the binding in the atomic nucleus. This is already an effect of the strong interaction. Binding energies in the nucleus are of the scale of 1 to 10 mega electron volts, which means temperatures of 10 to the 10 to 10 to the 11 kelvins. And the area that I'm focusing on today is the binding of these quarks in hadrons, like the proton. And the binding energy there is of the order of 100 MeV, so is again 10 times larger than the nuclear binding force or energy. And the temperatures are of the order of 10 to the 12 Kelvin. And at this temperature, you can ionize the hadrons. You can peel apart the quarks, and they become, as we say, quasi-free, and they form a new state of matter. That is the quark-gluon plasma. So the focus of our research in ALICE is to study this strongly interacting matter with many quarks and gluons, the quark-gluon plasma, and to understand how the properties of this plasma emerge from the underlying theory, how they connect to the properties of the particles. Now, there's a broader program, but this is the part of the program that I will focus on in the presentation today. And to give you a bit more of an idea of how we do that, so this is a theoretical calculation, a model of a collision of two nuclei. So you see here a red and a blue disk. They're not spheres, but disks, because they move towards each other at the speed of light, so that they're Lorentz contracted. And then if I switch on the movie, you see they will collide. And in this model, we then switch to a fluid description. So these contours are temperature contours of the quark-gluon plasma, which behaves like a liquid. And you see that it expands both longitudinally and transversely, and it cools down. And as it cools down, it freezes out into hadrons. So the particles that we in the end detect are what here are the white spheres. They are protons, kaons, and pions. They're the different types of hadrons. And the trick then of our field is to take these particles that we can measure in the detector and to understand from that what happened in the collision and what the properties of the plasma are. And I'll try to give you a flavor of how that works. Now, first would like to still introduce you to our instrument. So we already mentioned the Large Hadron Collider. You see here on the left an aerial picture of the area near Geneva in Switzerland. Here on the right, you see the airport for scale. What you see here is the Large Hadron Collider ring, which is 27 kilometers long. It's drawn into this picture. It's underground, so in the landscape, you don't really see the collider. You only see the access points. There are 4 large experiments at the Large Hadron Collider. There's ATLAS, LHCb, CMS, and ALICE. And ALICE is the experiment that I'm the spokesperson of, so I will talk only about this experiment. The different experiments have slightly different focus in their physics program and also slightly different designs. And the collision energy that the LHC, which is the most powerful collider in the world, provides is in proton-proton collisions. We started at a low energy of 7 tera electron volt, but now we collide protons at 13.6 tera electron volt. And for lead-lead collisions, we normally give the collision per nucleon or per nucleon pair, and we started at 2.76 and we are now at 5.36 tera electron volt per nucleon pair. It's important to remember that the lead nucleus has 208 nucleons, so the total energy in a single collision is 200 times this energy. So the total energy is much larger than in a proton collision at the LHC. And then on the right, you see some pictures of our detector. This orange thing, the outer thing, is the magnet, which we actually inherited from a previous experiment called L3. It's a normal conducting magnet. And here it is empty, and you see that we installed our detector systems, which have a characteristic shape. They surround the interaction point, so the collisions happen here in the middle. And one of the elements that is closest to the interaction point, you see here, this is the beam pipe, which is where the beams come in and they collide. What sits around it is a large silicon detector, and this is our recently upgraded detector. This is a silicon pixel detector with a total of 10 billion pixels in 7 layers. So it's a very large, very precise digital camera, maybe not unlike what you put in a telescope, if you want. Of course, our focus here is to detect charged particles, while you probably look more at light, but the technology is very similar. And to give you an idea of the timescale, so the experiment was conceived, it was the first discussions of what it should look like started in '93, and then a lot of development and technology development and amassing like a collaboration happened. And these first detectors were installed in the year 2006 to 2008. Then the LHC started operating, and as I mentioned, we did major upgrades a few years ago in 2020. Now, a bit more of a view still of the detector. So this is now a sketch of our detection system. I won't try to explain all the elements, but to orient you a little bit, here in the middle, you see this inner tracking system. That is this digital pixel camera, which I already mentioned. Then around it is a large volume. The blue thing is what we call a time projection chamber. Is also mostly to track the charged particles, to see their trajectories as they come out of the interaction point in the middle. And then around that sit subsequent layers of detector that are used to identify particles, to measure the velocity or the mass and things like this, to be able to tell apart the electrons from the protons, but also their pions and kaons and other particles that you can identify that way. And then the very outside there are calorimeters, which are mostly measuring very high energy photons, so GeV range photons. And as you can see, the detector has, so what I now described was what we call the central barrel, which is the part that sits around the 90 degrees, so to speak, from the beams. And there's a separate detector element, which is the muon arm, which detects muons, which are like heavy electrons, which are identified and detected in this direction. The difference in direction is just technical, practical. So we decided to build the muon detectors in the forward region and the other detectors at what we call mid-rapidity. And I'll show you some results of this without now going too much into detail of how they are obtained, of course, but to give you a flavor of how we do our physics. Now, before diving into that, one word about the ALICE collaboration. So this detector is an international collaboration, it's built by an international collaboration. At the moment, we have about 2,000 members, about 1,000 scientific authors, which are the PhD students, the scientists, staff scientists, postdocs, and senior engineers, with 157 member institutes from 40 different countries. And there are 5 institutes in Mexico who participate, about 30 people, so that's 3% of the total. Many other countries have similarly small, because if you divide by 40, then each country typically has 2-3%. But some countries have a much larger stake in ALICE. And here you see a picture of a recent meeting that we had. We have a few meetings per year where we meet and discuss our program and plan ahead. And this was at CERN in March. And to give you an idea of what we do with these 1,000 people, so far we have produced 500 papers starting from 2010 when we took our first data. And these 500 papers, of course, cover a very wide range of topics, not only the Coulomb plasma, but also other areas of what I would call multi-body dynamics of the strong interaction in proton-proton collisions, specific things like ultra-peripheral collisions, and also the properties of these hadrons and their interactions. Now, this I all will not cover today because that's just too much to fit in a single talk. Now, this is then a picture from a collision as we take it with our detector, of course, rendered in a rather beautiful way. So you recognize the structure of the detector that I just explained to you. Here in the middle is this inner tracking system. The white lines are tracks of charged particles that are measured and reconstructed by our detectors. And as you can see in a lead-lead collision, we get thousands of particles. In particular, when the collision is head-on, you get thousands of particles. You can also have non-central collisions where the nuclei partly miss each other, and then you get less particles. And here in the front, you see this muon arm, and that has fewer particles because the only tracks that you see are the muons. The rest is filtered out by an absorber that is placed here. Now let's dive a little bit into the physics. So the first question that you might want to ask is, so do you know the temperature of this plasma that you're creating? Because you said it should be 10 to the 12 Kelvin. But this is more difficult to measure directly than you think. And these are our current state of results. Of course, the way to measure temperature is by looking at the emission of electromagnetic radiation at light. So here on the left, you see measurements of the direct photons, the function of their momentum. And you see that the distribution is close to exponential, which is what you expect for a thermal emission source. And the temperature that we find with these photon emissions is about 350 mega electron volt. And this is in this 10 to the 12 Kelvin range that I mentioned. Now, one thing to keep in mind is that these temperatures are somewhat blue shifted because the source expands. So the apparent temperature is a bit higher than the actual temperature in the local rest frame. So what we would like to do is actually use dielectrons, electron-positron pairs, which are virtual photons. A photon can split into an electron and a positron. And that has the advantage that you can suppress backgrounds from hadron decays, but you can also get access to the unblue shifted temperature by measuring. This is now the mass distribution, and what you want to measure is the slope here in the middle. But one of the difficulties, or the main difficulty with these measurements, is that electromagnetic radiation is relatively rare. The hadronic particle production is 10 times more abundant. And some hadrons decay electromagnetically into photons or plus and minus pairs. So those you have to subtract for this measurement. So at the moment, we have an idea of the temperature, but not a precise measurement. That is how I would summarize this. Another way to measure the temperature is to look for things that melt in the plasma. And the main candidate for these are bound states of heavy quarks. So here you see a sketch of a charm and an anti-charm quark. And if they are bound, they form a meson that we call the Gibbs-I meson, which also has higher states. There's a similar state with the beauty quark, which is a bit heavier, and then we call it an upsilon. And what happens now, if you put this in a quark-gluon plasma, then there are so many charges around, color charges that interact with them, that they screen the charge, the binding force, and that melts this bound state. And the way we characterize this is by plotting what we call the nuclear modification factor, which is the production rate in heavy ion collisions, in lead-lead collisions, divided by the production rate in proton-proton collisions. And then here you see a result of that measurement with BB bar states, this upsilon that I mentioned, as a function of centrality. So these are large systems, hot collisions. On the right and on the left, you have the peripheral collisions, which are small collision system, lower temperature. And what you see is that there's a suppression pattern that at very peripheral collisions, there's almost no suppression. This ratio is almost 1. And then as you go more central, you have higher temperature, more and more is lost, is molten by the plasma, dissociates in the plasma. And this effect is stronger when you go to the excited state, the epsilon 2s, the blue points are below the red points. So the melting temperature of these mesons depends on their binding energy. Now we did the same measurement with charm quarks, which is shown here. So the plot is the same layout, peripheral to central, and then this ratio, which you see, the black points are from the relativistic heavy ion collider, which was at lower energy, where you see a very similar pattern, an ongoing increasing suppression. Well, now at the Large Hadron Collider, we found that this suppression kind of saturates, and then the ratio becomes constant, which is not what you expect with higher and higher temperatures. It turns out that at the LHC, we produce so many charm quarks that we can that there is a recombination mechanism. So we have dissociation, but also regeneration of these bound states. And that you can see best in this plot, where we now look again at the RAA, this modification factor for the J psi as a function of transverse momentum. And you see that at RIC, this was constant and at large suppression. At LHC, we see the same at high momentum, but at low momentum, there is an increase, which comes from the fact that at low momentum, you have many charm quarks and they can recombine and recreate a J psi. And that is a new phenomenon at the LHC. And this is now the latest result of that type, where you see that, these were our first measurements. Our recent measurements are much more precise. And we measure now at forward rapidity with this muon arm, those are the blue points, as well as at mid rapidity with the other detectors, the red points. You see that this increase is larger at mid rapidity because you have more charm quarks at mid rapidity than at forward rapidity. So this all hangs together with the picture that I mentioned of dissociation and regeneration. Now, the last thing that I wanted to show of our, let's say, physics program is this. It's quite a different approach to the collision. So here we will look for pressure gradients for the expansion of the system. And to understand that, we go back to the initial state. So this is a sketch of the two nuclei that collide. And when they collide like this, non-central collisions, the overlap zone is an ellipse, an approximate ellipse. In fact, when you think of nuclei, they have protons and neutrons inside. So they form a very irregular overlap region, which you can then characterize by spherical harmonics. So the main harmonic is the second harmonic, the elliptic shape, but there are higher harmonics, the third and fourth order are all present, and even the higher ones. Now, when this system expands, it will expand faster in the directions where it's shorter, because the pressure outside is zero, and in the middle it is a single value. So the gradients are large in the short directions and lower in the long directions. So you get a different push in the different directions, which means you get a different momentum distribution of particles as a function of the angle. And that is what we can measure with our detectors. This is a picture. This is the angle distribution of produced particles in a single collision at the LHC. And you see that the distribution is not quite uniform. There are these ups and downs which come from this expansion process. And you can actually see multiple, the second and the third harmonic in this picture. Now, to get more precision, you don't look at one collision at a time, you add all the collisions together, and then it looks like this. And you see very clearly that the third harmonic is very present with 3 peaks. The second harmonic is also present, and if you analyze this, you find that even the fourth harmonic has a significant amplitude in this picture. And the way we then normally report these results is by giving the harmonics, so that the amplitude of each of these harmonics as a function of transverse momentum for different particle species. And this is an overview of our results in that area. So what you see here is the function of transverse momentum, the second harmonic, so the elliptic distortion, if you want, for different particle species. And the pattern that you see here at low transverse momentum is interesting, because what you see is that as you go from light to heavy, so pions are the lightest, are in black, and then in the middle you have kaons, and then you get protons and lambdas, which are the heaviest here in this panel. You see a shift towards higher momentum, and this is exactly what you expect from an expanding fluid, because if you have a fluid element with a given velocity that freezes out in particles with different mass, the heavier particles will have a higher momentum than the lighter particles. So that is the signature that you see here. And we even, so I said this goes up to lambdas which have a mass of about 1 GeV. We even measure this for light nuclei, for deuterons, and now we have results for helium and for even heavier light nuclei, and they all show this flow effect. So they all flow with the plasma or with the fluid that expands. And then we also measure this for the higher harmonics, the V3 and the V4. I won't go into detail for that. Now, and then one thing we can do with this, or what the theorists can do, is they can use this to determine properties of the plasma. So they can, by combining a number of measurements, they can fit a model, and they can extract things like the viscosity of the Coulomb plasma, so the internal friction, if you want. And these are the results from such a fit to a larger set of data. Some of the data I showed and a few other things. And what you see here is that this is the shear viscosity divided by the entropy density as a function of the temperature, and it is about 0.1, and it slowly increases. Now here at the bottom you also see the bulk viscosity, whereas you see with the current data the precision is rather limited. So that's the viscosity that's associated with isotropic expansions. But what you can do with this shear viscosity, now you can compare the values that we find for the Coulomb plasma with, for example, helium near the phase transition and water near its phase transition. And you see that the plasma is much less viscous than the more familiar materials that we know. And that has, of course, to do with the fact that the constituents are much smaller in this Coulomb plasma than they are in atomic matter. Because maybe somewhat counterintuitively, viscosity is low when the interactions are many. So when the mean free path is short, you get a low viscosity. That is what this equation gives you, which you probably learned in statistical mechanics. So eta, the viscosity, is proportional to the mean free path. Small mean free path, small viscosity. So we see many interactions in the Coulomb plasma. So this was my kind of brief overview of what we do with our studies of the Coulomb plasma. And now I will return a bit to the instrumentation, to what we plan for our future detectors. So here you see a timeline of the Large Hadron Collider. We are now in 2024. We are in the middle of what we call the round 3 of the Large Hadron Collider. In almost 2 years, we will have another break in the operation, so we don't get collisions, but we will have time to upgrade the detectors. And we have plans for 2 new, relatively small upgrades. One is a forward calorimeter for photon measurements, and the other is a replacement of the inner layers of this inner tracking system with a very light technology, and I'll show that in a bit more detail in the next slides. And then we start again data taking. We have a run 4, and then we have another long shutdown. And in this long shutdown, we plan to replace ALICE with the next generation experiment that was in the title, with ALICE3. So this our plan is to install this in 2034, but it means we have to start doing R&D and design and already preparing for construction now, because building such a new system, it takes time, and we design and build our own detectors in this field. And I'll explain in more detail what that looks like. Now first let's look at this forward calorimeter. The forward calorimeter is a compact detector of about 1 meter by 1 meter, which sits around the beam pipe. The interaction point is here and measures photons that are at forward rapidity close to the beam pipe. And this gives access to the understanding of the structure of the nucleus. Here on the right, you see a projection of the precision of the measurement of photon production and the impact on the structure measurements, which I won't go into too much detail. But what I can show you in a bit more detail is the technology that's involved. So this calorimeter consists of 3 pieces. There is a hadronic calorimeter that is used to reject photons that come from hadron decays. These are copper tubes with scintillating fibers inside, read out by silicon PMs. Here you see a picture of the current prototypes. We are now moving towards production of these things. Then you see this forward part is the electromagnetic calorimeter, which consists of layers of tungsten and silicon sensors. The tungsten converts the photons into electrons and positrons, and the sensors measure those. And most of the detector consists of these pad layers, which have sensitive areas of about a square centimeter, and these are 72 on a pad. And they will be coupled to electronics on such a PCB. And then there will be 2 layers with very high granularity using pixel sensors, which are mounted like this. So these here you see each of these kind of 1.5 by 2.5 centimeter areas is a single pixel chip with I think 1,000 by 500 pixels, 30 micron by 30 micron each. And then this yellow stuff is our readout cables that are going here to the side where you can take the signals out. And what that allows us to do is to see with very high resolution 2 photons also when they're close together. That's what you see here in the middle. This is a picture taken with a test beam with this pixel layer. And you see here that at a distance of several millimeters, you can already see 2 photons, 2 of these high energy photons, even if the total energy deposition is rather spread out. So that is one of the design requirements of this forward calorimeter. Now, the other upgrade that I mentioned is this inner tracking ITS3, the 3rd inner tracking system. Now, this is not a replacement of the whole digital pixel camera, but only of the inner layers. So you see here 3 green sensor layers. And the idea here is that we take silicon, which is, as you probably know, normally is a bit like a glass. It's very brittle and it breaks easily. But if you thin it down to 50 micron, it becomes pliable, it becomes flexible. And so we make very large sensors. I'll show them in the next slide. And we curve them around the beam. And then the advantage of that is that we don't need much material to support. So we have very thin, very light structure. We can go very close to the interaction point. And with that, we get a very good, what we call pointing resolution, good resolution on the spatial coordinates of the track close to the interaction point, which is good for measurements of heavy flavor, of charm baryon decays, for example, for which this is a performance plot. And here you see then the device. This is not the final device. This is a kind of a test of this concept. So this copper-looking thing, this is actually a sensor, a silicon sensor that is curved around the mandrel and then bonded to PCBs to demonstrate the technology. Now we are now in the phase of really making this a reality. So design of the sensor chips and the readout system are already advanced. And what you see here is, this is a 12-inch wafer where you see that somebody takes out a narrow strip. This is still a test structure, but it is 26 centimeters long of interconnected silicon sensors. And they will be treated as one. Now the goal is in the end to have these kind of 26 by 10 centimeter single sensors, which have connectivity on both ends, one for power and the other for the readout. And the design of this final sensor is now progressing. We plan to submit it for fabrication early next year. And then here you see also some newer prototypes of the mechanical structure and the electronic connections. So this is the type of development that we are doing now for the near future. And this is the type of development that we would like to take a step further in the further future. And so this ALICE3 that I mentioned before, the new complete upgrade of the ALICE detector, the concept is that it is a compact detector in a strong magnetic field. Our current detector is rather large. It's 4 meters radius in a weak magnetic field. So it's quite a change of approach. And to do that, we will build 10 or 12 layers of silicon pixel sensors for the tracking. And something that's also new in ALICE is that we will instrument also the forward direction. So we will cover a much larger spatial angle, not only kind of 45 degrees around the perpendicular, but rapidity 4, we normally call this. And the other thing is that we would like to, again, improve the pointing resolution. And to do that, we need to go closer to the interaction point, closer to the beams. And this requires a very special setup because when the beams are at high energy, they're very focused and you can go to a few millimeters from the beam. But when they are injected, when the beam enters the machine at a lower energy, and they're less focused at that moment, and then the detectors need to be farther away from the beam. So what we're working out is a retractable system. It's a system that can open when you put in the beam into the accelerator, then you accelerate, and then you close the detector so that you can be very close to the beam. And then you have, on this plot, this is kind of a characteristics plot of the detector. So the pointing resolution has improved already in the last years, and with this ITS3 it will be even better, but with this ALICE3 it will still be a factor of 3 to 5 better in the future. And similarly, the acceptance and the interaction rate that we can process will keep improving so that we can look for rarer and rarer signals of the plasma. And I would like to briefly go back to a few physics motivations for this setup. So one is this thermal radiation that I already mentioned, which I mentioned is a rare process and has a large background. So it helps if you have more statistics. It also helps if you have better pointing resolution, because then you can reject one of the main backgrounds. Now here on the left, you see a plot that motivates this measurement. This is the collision energy on the horizontal axis. The vertical axis is temperature. Most measurements, as I mentioned before, are using hadronic observables, but they give you at high energy, they show just the phase transition temperature, the 150, 160 MeV, so they don't tell you about the plasma temperature. And to measure the plasma temperature, you need electromagnetic radiation, and you see here existing measurements at low energy, and you see that at RIC, they have measured it, but the uncertainties are very large. And here you see a projection of our measurement with the new detector. And here you see how that is done. So this is this mass spectrum that I showed before. And with ALICE3, the error bars will be very small. And this, the slope here at the in high mass gives the temperature. And with this precision, we can even do things like measure this azimuthal anisotropy that I mentioned for the other particles before of the thermal radiation. So we can measure the expansion velocities before the plasma freezes out. Then another part of the program is to measure interactions of heavy quarks with the plasma. And the golden way to do this is to take pairs of a charm and an anti-charm quark, which are produced back to back, so 180 degrees from each other in azimuth. And in this plot, that is shown as this blue peak. So at pi, there is a large peak because they go back to back. But when they interact with the plasma, they get scattered around, and this peak is suppressed. And so to measure this, or this we can measure with ALICE3, and I again have this is a projection of the precision that we will have in with the new detector. And you see that this is very precise, where you can measure the amplitude and the width of this wayside peak very accurately. And with the current system, the measurement would look something like this. So we have no resolution because we don't have the pointing resolution and we don't have the statistics at this moment. So this is another goal of this upgrade. Now, the last example that I would like to give is the measurement of what we call multi-charm baryons. So I mentioned before that we produce enough charm quarks in these collisions to reform multi-charm particles. I mentioned the JPSI, which is charm and anti-charm. A more clean probe is to measure particles that have 2 or 3 charm quarks. So the one is the Xi-CC, and then the triple charm is the omega triple C. And they have a characteristic enhancement pattern in heavy ion collisions. So far, we've only measured single charm. So we've only measured the bottom, the middle line here. And we want to measure the higher lines because this tells us about, let's say, the freedom of movement of charm quarks in the plasma. And to do that, we look at displaced vertices of Xi strange baryons. And this is just to show again the precision with which we can measure that. So this is for the Xi-CC and the omega CC, the precision of a measurement with the ALICE3. Okay, so there was one more thing, which is the melting and regeneration of the quarkonia, which I already mentioned before. But what we would like to do with ALICE3 is to go to higher states, which we call P-wave states, and they have names like Chi-C and Chi-B. What you see here is a theory calculation of these mass peaks of the bound states and how these change as you increase the temperature. So the different lines have different temperatures. So that is the melting that I mentioned before. Now, without going into much detail, I wanted to show you again some performance plots which show that we can measure these Xi-C states, which haven't really been measured. We know they exist, but we haven't measured their production rates with ALICE3. And for this, we use a muon detector, which we will, in ALICE3, we will have a muon detector in the barrel, so in the mid-rapidity range. And that's actually also a project that some of the colleagues in Mexico are working on. I'll have one more slide on the test beam activities that have been happening. Now, and then with that, I will give you a little bit more flavor of how we approach this, about the R&D and that is going on for the different detector systems. So this is this retractable vertex tracker that I mentioned at the start. So what we are doing at the moment is to look at the mechanical principles for this retractable tracker. This thing has to sit inside the vacuum because it's close to the beam and the beam is in vacuum. So one thing that we also do is to characterize different materials for their outgassing, for how well they behave inside vacuum. And here you see a first mechanical prototype of this retractable tracker with an idea of how you could operate it. So you need to operate it from outside the vacuum and transfer that to inside the vacuum. So there's a whole technology to develop there. This then will be instrumented with sensors which are similar to the ones for the ITS-3, but should be a next generation. Now, since we want to instrument a very large area of silicon sensors, we're also looking at ways to industrialize processes. So in particular, at a way to put many of these sensor chips together on a PCB or a flex PCB to make large modules so that you can more efficiently tile your surface. So this is a concept for what we call a ladder. So this would be something like 10 centimeters wide by a bit more than a meter long, tiled with sensors. And here you see tests that we are currently doing with a company in Korea to pick and place these sensors and to produce these modules. And okay, this is still also in the R&D phase. We're trying to see what is possible in this area. And then finally, for the tracker, also we also have to look at other things like the cooling. How do you? This is all electronics that all consumes power, and it needs to stay more or less at room temperature. And we are doing studies for an air cooling system that cools this. These are relatively low power sensors, so by directed airflow, we hope to be able to cool the sensors without needing to introduce water pipes, which water by itself is okay, but water pipes are relatively a lot of material and this interferes with the measurements that you do. So air cooling is in that sense a good solution. Two systems for particle identification, or several systems, but the two for the hadrons are the time of flight and the RICH system. Time of flight measures just how long a particle takes to go from the interaction point to the sensor, but you need a resolution of about 20 picoseconds to be able to identify particles. And the RICH is a ring imaging Cherenkov detector. And the other particle identification system are this muon identifier that I mentioned before. So that sits here at the very outside. So you have here, this is an absorber that blocks all the other particles. That is this big block. And then on the outside, you see two layers of sensitive elements to detect the muons that come out of this system. Of course, you measure the start, you measure in the inner tracker, and then it goes through the absorber, only the muons go through the absorber, and you confirm that it is a muon by measuring them on the outside. And then we've also, we have plans for an electromagnetic calorimeter, which would be installed here in the middle, somehow between the tracker and this muon identifier. And this gives an impression of how these different systems work together to identify different particles in different momentum ranges. I will not go in detail, but it is there for reference. I wanted to show a few things about the R&D that we're doing. So this is for the time of flight system. For the time of flight system, what we want to develop is a similar pixel sensor to the one that I showed you for the tracker, but then one that can also measure the arrival time. And for that, you need high amplification in the sensor. And we are doing a prototype program together with, this is driven by INFN in Italy, but also with some collaboration with the groups here. So you see here now current measurements of the gain as a function of the voltage that you apply externally, and a measurement of the time resolution. This is very fresh. This is a test that was done in June this year. And here you see that the time resolution is there's a correction about 75 picoseconds. But I mentioned earlier that our goal is to reach 20 picoseconds. Now, what we plan to do as a next step is to thin these sensors. So these sensors are still 50 micrometers thick, so they're thinner than a standard wafer, but we want to go to 20 microns, and with that and a bit more gain, we think we can reach the 20 picoseconds, but this is the ongoing R&D. Now, then for the ring imaging Cherenkov detector, you see here again, I think I swapped the slides. I wanted to show first the concept. So a ring imaging Cherenkov detector, you use a layer of, in our case, aerogel, where the particles go through and they produce Cherenkov radiation. They produce light that comes out in a conical pattern, like a Mach cone shock wave of an airplane. And then you image this ring using, in our case, silicon PM readout planes. And to instrument the whole surface, this is the design that we are currently having. So we have a projective geometry. We have modules that all point back to the interaction point. So here they are 90 degrees, but they are under an angle, and the aerogel is this front, and then here in the back will be the electronics. And here you see some studies that we're starting to do for how we can integrate readout electronics and silicon PMs in a readout plane in such modules, and to have a continuous instrumentation. Now, and this is then a test of a prototype. So here we test more the concept. So we have in this device, there is this aerogel, and there is a readout plane with silicon PM sensors. You see here they are mounted somewhat apart because we have a very controlled system for the beam. What you see here is the measurement. So the beam is always pointed here at the middle, and then you see very nicely a ring, and the angle of the ring depends on the type of particle. And you see here a measurement of the ring angle for pions and protons at a given momentum. And what this shows is that we actually already reached the design resolution. We reach an angular resolution of 5 millirad, which is better than the 6 millirad that we need for our system. So then the last R&D item I wanted to show is for the muon identifier. For the muon identifier, we are considering several different technologies, multi-wire proportional chambers, resistive plate chambers, and scintillators. Scintillators are currently the baseline option, and this is what colleagues at UNAM and other institutes are working on. So you see here the scintillator bar with the wavelength shifting fiber, which then produces the light. When a particle hits this, you get a flash of light, which you can measure with the silicon PM. And these are test results which show that the efficiency of this is very high. And this shows the charge or the signal amplitude distribution, which is characteristic of the process that you get from energy loss when you go to a scintillator. So this looks already very good, and also here the performance has been demonstrated. Okay, so with that, I would like to wrap up. I see that I left 2 draft slides inside, but I wanted to go to the summary. So I hope that I've shown or introduced to you the fact that ALICE is a general purpose instrument for a multi-particle QCD measurement, and I try to give you a flavor of the things we do, especially in this Quark-Gluon plasma, how we measure the temperature, how we measure these pressure gradients and the expansion and the melting of certain states in the plasma. And then I introduced to you the ALICE3 concept, a new detector, and the work that's going on to make this a reality. So there's a big program in ALICE, not only of the, let's say, the fundamental physics that we're doing and the data analysis, but also the construction and development of future upgrades and of new types and classes of particle detectors. Thank you for your attention.
Thank you very much, Marco, for this really interesting, I think for many people also like introductory talk into the particle physics and everything that's going on in high energy physics nowadays in CERN in particular, and in ALICE in a more particular manner.
Yeah.
So now we open the session to questions. Also to the people following us on the net, we'll see later on. Please.
Hello. Hello, thank you for being here. I have 2 questions. For first, could you talk more about the plasma conditions, the characteristics, and storage?
And storage?
Yes, the storage.
So this plasma, the plasma that we study is a strongly interacting plasma, and we cannot store it. Yeah. What you might be thinking of is if you have an electromagnetic plasma where you ionize atoms, this you can store in magnetic fields, but we don't have color magnets to keep the plasma inside. So what happens is you produce it in the collision, it expands, cools down, and what you measure are the products of the hadronization of the freeze out of the plasma.
Okay, yes, I have. I need to know
No,
that.
it's a good question. I just wanted to explain a bit better how this.
Do you have a simulation data to compare the laboratory data? On what kind of programs do you use?
Yeah, so we have different levels of simulation. So one thing I'm trying to find, I may have no, it's not there. Just 1 second, because I have, maybe I really took it out for this audience. No. So when I showed you this part, about the elliptic flow. I showed you also this slide. And here what has been done to get these curves is that you take model calculations that do the whole collision and the expansion, and they predict the measurements that we have here. And you run this model with different parameter settings, many of them. And then by comparing to the data, you keep only the ones that are matching the data, and that is what determines this line. So this is what we call a Bayesian inference. It is kind of a fit using a specific technique, this Bayesian inference, using hundreds or even thousands of model settings, and then picking out the ones that are in agreement with the data. So this is one way to determine the physical parameters from the measured results. And so this is one element. The other element where we also use models and simulation is to correct what we measure to the physical truth, so to speak. So the detectors have efficiencies and they have their backgrounds in the detector. So to simulate this, we have a package that is called GÉANT, and it reproduces detector response. So it tells you where you put in, when a particle goes through, how big is the signal, and then you run again the reconstruction on the simulated event, and from that you determine things like what we call tracking efficiency. So how likely is it that if there is a particle, that you also see it in the data, and these tracking efficiencies are normally of the order of 80 to 90%. So if the particle goes nicely to all your detectors, it's very high. If it is a little bit goes through the cracks, then it's a little bit lower, and that is all you need to correct.
Okay, thank you. Do you see difference between, first, do you do a simulation of protons and electrons, and do you see difference between the hadrons and quarks, or similarities?
So we do simulations both of proton-proton collisions and of heavy ion collisions. These are often a bit different models because the proton-proton collisions, those models are developed for one single interaction, while in a heavy ion collision you have many interactions going on. So the way this is done, this is implemented, the physical model is a bit different. So that is on the, let's say, the physics side, the fundamental physics side. And then, of course, the different particles give different response in our detectors. That is how we identify them. So there's one detector here, which I didn't really discuss, this yellow thing. This is what we call transition radiation detector. And that means that it's sensitive only to particles, or the transition radiation comes from particles that are very close to the speed of light. In our case, electrons give a specific signal in that detector. So it's made to identify electrons. Another thing is that in these calorimeters, electrons and photons give a very high signal, but pions and kaons do not. So these are tricks to identify particles.
Okay, thank you so much.
Thank you for the question. Any other question here from the audience? From the floor? Okay, then maybe I just wanted to comment a little bit of what do we do here? So where do we participate? Because all of a sudden I was asked, so okay, where are you? Okay, so basically here at NAOE, we're a group of around 12 researchers collaborating with ALICE3 upgrade, and we are participating basically on the RICH, so ring imaging Cherenkov detector. And basically, it consists of several layers and several issues that have to be solved. And as Marco really showed us, it consists of a Cherenkov radiator, which is based on air gel. And one of the problems with heavy ion collisions is that you have really many different particles going around, and you want to identify them. So what we do is these particles interact with this air gel, and depending on the energy of the particles, they will produce these Cherenkov flashes of radiation that will can be imaged as circles with different diameters, okay, 20 centimeters away from this Cherenkov radiator. So we see it here on the left part. And what we have on the detector side are actually silicon photomultipliers, because we want to have photodetectors are really fast, can detect really nanosecond long flashes with really few photons being generated in each flash. So the silicon photomultipliers are actually the technology of choice for that kind of things. And just to understand the complexity of the thing, we have these 24 rings, which you see here. The inner diameter is 90 centimeters, the outer diameter 120 centimeters. And each of these rings has 24 segments. Each segment has a size, now we discussed it last week, by the way, it's 17 times 18 centimeters, which we're going to be having. And on each of these segments, we have 6,912 silicon photomultipliers. So if you basically multiply 6,912 CPMs times the 24 segments per ring, times 24 rings, you end up with around 7 million CPMs that can be or must be read out simultaneously in a really short amount of time. And this is the complexity of this entire thing. It has 7 meters, no? It's going to be 7 meters long, all these 24 rings put together. And the entire detector has to be held at minus 40 degrees centigrade. So we don't have models for electronics at that to start with at that temperature. We are working on that, and of course we have a lot of power, electrical power generation. So we still don't know. This is one of the big issues. How are we going to keep the entire system at minus 40 degrees centigrade at that time, and how at that temperature? And on the other side, we are going to be use these CPMs that actually we are trying to design a new technology. So we are working with Bruno Kessler, Foundation Bruno Kessler in Italy, and for the time being, and we are trying to develop new CPMs so that we can improve the photon detection efficiency of these detectors. And on the other side, they have to be connected, and you see here through something that we call the PCB interposer. And on the other side of a PCB, we are going to have ASIC, application-specific integrated circuits that we are working on. And they need to have a timing resolution of below 100 picoseconds. So it's challenging on so many levels, because at the end, all these detectors, we were forbidden, and this is one of the big issues, to have FPGAs put there because of the radiation hardness. So we have lots of high energy radiation going on and affecting the electronics. So the FPGAs had to go out. And if the FPGAs go out, then we need optical fibers to connect the FPGAs, which are outside of the detector. And this means a lot of connectors and really complex systems on the PCB levels going down as a stack. And just to finish with this, and then they told us that there is not much place. We only have 4 centimeters for the entire front-end electronic stack. And so that's our headache.
So we like to make our life very hard, but it's we push the technology. I mean, these particle physics experiments, they to some extent develop their own technology. They push the technology for every next generation of experiment. You want to be better than in the past. And now we have all these wonderful electronics possibilities with silicon PMs, with application-specific ICs. So we try to push this to the maximum for the next generation of experiment, and that way we get better and better at what we do. And of course, this is something that happens in a big collaboration where different people bring different expertise. So the cooling can be brought by, and can maybe be brought by but maybe also by some other institute. The radiation hard optical connections or optical transmitters have been developed at CERN, and we use them for the system, but of course they need to interface with each other. So this is the type of challenge that we like to undertake to push our detectors, which then also has applications in many other places. In astronomy, I assume, I don't know, I'm not an expert, and even in industry. So our pixel sensors are being produced by a company that also produces LiDAR sensors for self-driving cars, basically. These are distant measurements devices that are now quite common, but it is it was developed at some point. LiDAR is a technology that I think was also developed by scientists and now is used in cars, and you can buy a chip that just tells you the distance. Mm-hmm. So this is the journey that we're on all together.
Yeah, thank you. So Okay, this is just as a comment to see what the complexities are on each of these different. So there are 6 detector layers, and each layer has its own particularity. And of course, the vertex, the pixel detectors, and this flexible electronics. It's beyond what we could have imagined like 10 years ago. So it's actually right now it's over the state of the art. So nobody does it still, and so it's going to be really challenging. So I think it's a wonderful journey, and I would really like to use this opportunity also to invite any master students or PhD students who have some interest and would like to tackle all these problems with us, just to join, to maybe approach any of us working in here on these problems, and even right now today, if you want to ask something, Marco. So he's going to be here a couple of hours more. We're going to show him around the labs, and I think it's quite challenging to be part of this. So it's also a high, let's say it's a real pleasure, and it's a real honor to be able to be there and contribute somehow to with all these developments. Then later on, as Marco just said, can be used for any other applications. No? So that's more or less the message. I don't know if there is any other comment from the audience or from the internet. Here we are. Yeah, that's good.
Experiment again. With the instruments in the collider, you can identify all the particles product of the experiments.
Yeah, so the detectors, the primary function is to measure the momentum of the particles by measuring their trajectories and the curvature. But then, as I mentioned, so here you see an example. So this is with the ring imaging triangle detector, which for now we have only a small one. But what you do, so here you see as a function of momentum, the ring angle. And so you measure the momentum with one detector and this angle with the Cherenkov detector. And then you can see that for different particles, which have different masses, this angle, the behavior is different. So what you do, you measure the momentum, for example, at 5 GeV. If you measure this angle, you know it's a proton. If you measure that angle, you know it's a kaon, and so on. Then you see at some point, you run out of resolution. You can't tell apart a muon and a pion because they have very close masses. So, and this is one step. Now, then the other technique for identifying particles. So this is kind of direct identification. The other technique I showed a little bit here, which is decay reconstruction, also very important. Here it is. So what you see here is a schematic of the detector. These are the tracker layers. And you see here a particle that decays into 2 other particles. And then and actually what you don't see is that this is also a decay where some particle at 50 or 100 micron distance from the interaction point, it produced pions and this Xi. And so this is another technique to identify particles by identifying these decay signatures.
Thank you.
Yes. And there is one question from the audience following us online, and the question is, what software do you use for simulation? Which you briefly mentioned, but
so for simulation, our workhorse, I mean, for detector simulation, we have this what we call GÉANT, which is developed at CERN. I'm told it's also used in medical applications. If you do particle therapy, where you shoot beams on people to kill cancer cells, you also need to know how beams interact. So that's also used there, but we use it to simulate detector response. And currently, so we used to have for a long time GÉANT3, which was written in Fortran, and now we have GÉANT4, which is written in C++, but this is kind of the industry standard for this type of simulations. There's another package called FLUCA, which is more used for radiation simulations when you have a lot of neutrons and you want to irradiate things. It's a bit different specialization. And then we have a lot of different packages for the physics simulation of the collision itself. There's something called Pythia, which is an event generator for proton collisions, which is very well known, and there are several others.
Okay. Any closing last question, comment? No? Well, then we really thank you for this really interesting talk, Marco.
Yeah,
and
welcome.
Okay, we have a little present and and a certificate of recognition for you visiting INAOA, which we are really thankful for, so that you can.
I'm going to read this certificate of appreciation. Is granted to Marco van Leeuwen in recognition of his valuable contribution as a speaker in the extraordinary institutional seminar entitled ALICE3, The Next Generation Quark-gluon plasma at the Large Hadron Collider at CERN in the Electronic Science Department, conducted on November 26, 2024 in Santa María Tonancintla, Puebla, Mexico, and is signed by our General Director, Dr. Julián David Sánchez de la Llave. Thank you very much.
Thank you very much. It's a pleasure to be here. Yeah.